Hello folks, and welcome to another uber boring episode in our VCU series. This will be part 3, and I would strongly encourage anyone that is just joining us in this part to go back and view the preceding 2 parts, and I will put a link in the description to them. So, in part 2, we went painstakingly through a lot of the theory of our VCU and showed you all the wiring connections and explained the configuration menus on our web interface. Today we're going to get away from the theory and we're going to jump into some practice for you. So what we have here in front of us is essentially a complete what's called stack from a 2018 Nissan Leaf. So there's 3 parts to this. It's called the PDM up the top here. So this has a charger, a 6 kilowatt charger, and a DC to DC converter. Underneath it is our inverter. This is the 110 kilowatt version. And finally, down here is our EM57 electric motor. Now this setup I have been using here for some experiments, and additionally this is the system that I'm going to be using in our future conversion of our Mitsubishi L200 truck. But before I break this down and pack it away for that future project, it does make an excellent platform for us to basically show you in, again, rather excruciating detail how our VCU wires up to a system like this. Now, as we explained, the VCU can control a variety of these kind of systems, but this is just one example that we happen to have on the floor here in a reasonably ready to go fashion. And so yeah, what we want to do is we want to show you the basics of how this wires up and how we can run it. We'll show you things like software updating and throttle calibration procedures as well during this session. So, point of using systems like this really is so that we don't have to reinvent the wheel. We can get these nowadays for quite reasonable monies, and they are engineered for automotive applications, because that's what it is. Nissan did a lot of the hard work for us, so we can kind of jump in on that and use our VCU to enable components like this to be used in EV conversion projects. So let's jump straight in and have a look at our VCU. Alrighty. So here is our VCU. It's in its aluminium enclosure, and we have our connector attached as per our wiring pin descriptions from the last video. We come down here to this bundle, then it explodes out into this bit of a mess job here. But in reality, if we take this slow and steady, we take each wire individually, it's actually not that difficult at all. Here we've just got a 12 volt battery, which is a normal car battery that supplies low voltage power to our systems here, and of course to our VCU. Got some more wires and stuff going on here at the back. This is where we connect into our Nissan Leaf wiring, and I'll go through all that with you shortly. And here we have our ISA shunt. Now this one looks a little different to the one we showed you in the last video. It's a slightly older model, but works the exact same way. And down here then we have some contactors for controlling the high voltage. And you'll see here that I've got got a white, which would be our high voltage battery positive, and a black, which would be our high voltage battery negative. So, bit of high voltage wiring going on, and a bit of low voltage wiring going on, and we connect in there to our VCU. So let's start with our 12 volt battery here, as we would in a traditional, I suppose, wiring diagram for a car, and we'll break it down as easily as I can for you. One of the things folks always ask me about is, do I have a wiring diagram for this or a wiring diagram for that? And the answer to that is no, I do not. Because there's two reasons for that. One is I can't do everything. Because if I do one wiring diagram, I'll want three more. And it just tends to snowball a little bit. And the second thing is I'm absolutely crap at drawing. And I did actually try this with some of the Tesla stuff to draw diagrams. And then I tried to get a few professional people to convert those squiggles into actual, electrical drawings for me. But that didn't work out either. It ended up costing me quite a bit of money. So unfortunately, folks, that is not my forte. So we're going to have to go with what I can do here, and that is to describe to you this setup. And it's actually, once we get into it, you'll see that it's actually a lot simpler than something that you would do even with the likes of a standalone ECU for an internal combustion engine. Alrighty, so here we are. Most basic place to start is our 12 volt battery negative terminal. As in any system, this battery negative terminal, I just have it connected via a fuse to this cable, and it's going to chassis or ground or just bolted on to any convenient part of our system here. I then have this black wire here, which is again just attached to a chassis ground here, and this is our ground connection to our VCU. Coming across here, we have our 12 volt battery positive, and this wire is a thicker wire, again the same as this one, be a main feed. We come up onto our PDM, and this is our PDM battery positive, and so this is our 12 volt battery positive, and anything on the casing is our 12 volt battery ground. Here you'll see I've got two fuse holders with just, pop the cover off that, just little standard, I think 5 amp, just blade fuses in them. A lot of this is just for convenience here on the testing rig. So one of these has a little multi-block on it, and it goes off to various places, and I'll explain that in a minute. But we'll take the simpler one first. So this one just has a single wire, and I'll bring you around the side in a sec. But where this single wire goes is this just supplies permanent 12 volt power both to our PDM and to our inverter. So this fuse here just curls around with a bit of wire and gives a 12 volt positive feed, inverter and PDM. Simple as that. This wire here breaks off into a little junction block. So let's take each one of these individually. This one here is our 12 volt positive feed to our VCU. So we just come from the battery through a little fuse. This gives our VCU permanent 12 volt power. This wire here goes down to just a standard 4-pin automotive relay. And this relay is controlled by the VCU, and it lets it switch on and off the switched 12 volt feed to again our inverter and PDM. So when we're waking up our system, be it for charging or for driving, the VCU through a low side switch on the coil here can energize this relay and apply the switched power to our inverter and PDM. Those are the only power feeds that we need for our system here. So we take one more wire, two more wires off this. This wire here is going around the back and is supplying our contactor positive feed. So the 12 volt permanent DC supply to our contactor coil positives. And finally, this guy here goes up to a switch that you will just see crudely screwed onto the corner of the bench here. And we use that for supplying our digital 12 volt signals to the VCU. So things like terminal 15 on, so our ignition switch on, and our start signal, so our momentary switch to the start signal. And I'll run through that again in a bit more detail. But these are our basic 12 volt feeds here from our battery to our PDM, and via just one standard 4-pin relay for the switched feeds, and just via a fuse for the permanent feeds. And folks, that is as complex as we get here with a system like this in terms of just supplying power to it. The VCU via the white wire here controls the low side of the relay coil. So what I'm going to do next, I'm going to switch the camera around, and we'll bring you around this side here and show you where, for example, our 12 volt permanent feed and our 12 volt switched feed from the relay enter. We'll show you where we connect the CAN bus to our system here. So stand by. Stand by for action. Alrighty, so we're back around to this side where we've got a bunch of wiring and some connector blocks here. So let's start with the most basic one. This is just our permanent 12 volt feed. Naturally, it's mixed up with all of these guys. And it literally just goes to this 3-way terminal block and goes off to our two permanent 12 volt feeds. Again, one to our inverter and one to our PDM. So that's it. Secondly then, we have our switched feed. Let me find it here. Where's our switched feed? Here we are. This is our switched feed from our little 4-pin relay. And you'll see that that goes off to the two switched 12 volt feeds. We have this black wire, which is a ground, and it just goes to this brown wire here, and this goes all the way back around and just connects to somewhere convenient on the casing. And that, folks, is our lot for supplying 12 volts and ground to our inverter and PDM. Now the big question is, how do we control all this? Must be super complicated. And it is. There's a whole two wires. There's two more wires that we have to connect. Now let me just disconnect these, because this is a little monitoring system for CAN that I use here. But you guys don't need to worry about any of that, because it's not got anything to do with what we're trying to do here. So let me get rid of that. So what we've got is, from our VCU, we have a twisted pair here, which we call EV CAN. There's two wires in this. So this is our CAN external to high and CAN external to low. And they're in our, literally in our, just two wires. There's just a third wire in that, but we don't use it. It's just a handy bit of twisted pair that I happen to have. And we literally just connect CAN low here from our VCU to CAN low on our our original wiring harness, and CAN high from our VCU, the CAN high on our wiring harness. And folks, that's it. Congratulations, we're now driving a Nissan Leaf drivetrain, courtesy of our VCU. So we need to give it permanent 12 volts, we need to give it switch 12 volts, we need to give it a ground, we need to give it CAN high and CAN low from our VCU, and that is it. If you want to get super complex and we'd like to use the PDM for charging, then unfortunately there are two more wires that you need to connect. We connect those to our charging socket. So in this case we have our control pilot, or CP. This goes from here back to our charging socket, which we will show you later on, and our PP, or plug present wire, from here back to our charging socket. And that's it. Congratulations, you're now using motor, inverter and PDM with our VCU. Alrighty, so next thing we need to look at is our whole high voltage setup and how we control that with our VCU. Now this is not intended to be any kind of an educational segment for people on how to handle high voltage, because I ain't gonna touch that. But what we will do is show you for our very basic test rig here how we do it here. Now, as you'll see here, we've got these two black devices here. These are our contactors. Normally in a high voltage system like this, we would have three of them. We'd have one on our negative side, one on our positive side, and one for pre-charge. Now, in the case of my simplistic little test rig here, I'm just using two, a main positive contactor and a pre-charge contactor, and that's because this is only a temporary setup here. So if we look up here on the bench, we have our high voltage battery positive and our high voltage battery negative. We have our ISA shunt connected here to the high voltage battery negative. Then we come out of this with a cable that we bring to our PDM, and that basically distributes high voltage negative to our charger, inverter, DC-DC, and whatever it is that we would be using. This little wire here comes out of the V1 monitoring connection on our ISA shunt, and that connects into the PDM to the battery positive after the pre-charging system. So we connect our monitoring tab after our contactors and pre-charge, so that this guy is monitoring the high voltage that we're applying to our, I guess, drivetrain would be the shortened term. So contactor control is entirely via our VCU, and what we do is, again, let me just lean in here a little bit and you'll see I have a red wire that I spoke about earlier. This is just bringing permanent 12 volts from our fuse, from our 12 volt battery positive, into the coil positive terminals of our two contactors. And the two black wires then, that you'll see here, are being switched via the relevant pins on the VCU. So it being pre-charge, low side switch, and main contactor, low side switch. That's why we have a permanent 12 volts on our coil positives, and we switch on the blacks, or negative side of our coils. And we just have a crude little setup here then with our pre-charge and our main contactors, just using a heater element here for that purpose. And finally, we come out of this wire here, which is our high voltage positive, after our pre-charging and contactors, and go into our PDM. So what I'll do is I'll pop the cover off the PDM here, and you can have a look in here, and it'll hopefully make a little bit more sense of where we're connecting things. I'm not going to go into a huge amount of detail on this because, like I said, that is a topic entirely by itself. One thing I will just note is we have a little 4-core wire here going into our ISA shunt. So just to remind folks, the ISA shunt is our battery monitoring system, and it basically informs the VCU about voltage, current, temperature, amp hours, kilowatt hours, and all that good stuff. And it does that via CAN. So all we need to do, we have a red and a black wire here, which is a permanent 12-volt supply. And we have a green and a yellow wire, which is our CAN high and CAN low. And we connect those to the relevant CAN external 2 low and CAN external 2 high pins of our VCU. And indeed, they simply then come back down. So we're linking our CAN here from our drivetrain with our CAN from our shunt. So literally, that is it from a wiring up of a drivetrain and our shunt here. So I'll go ahead and pop the lid off the PDM, and we'll show you where the wires connect here, just to kind of familiarize folks a little bit more with that. And finally then we'll show you where our charging socket connects up. All right, just pop the lid off the PDM here. There we go. Okay, so let's get you in a little bit neater here. You'll hopefully be able to see some of the wiring. So you'll see here that I've marked these 2 copper terminals with a red and a blue, and I put a plus and a minus there beside them. Those are our main high voltage battery connection terminals. So this is where we come in after our contactors with our pre-charge and our main contactor. And this is our battery negative, which would normally be going to a battery negative contactor and then heading off towards our battery. You'll notice that there's 2 wires on the positive. And the reason for that is one of them brings in our high voltage positive, and the other one is our little monitoring wire here from our ISA shunt. So super simple. I'm going to talk to you a little bit about how we connect up AC charging to the PDM as well, just because we're here. It'd be a shame not to. So I've just got a piece of 3-core cable here. This is a single phase 6 kilowatt charger. So green and yellow, earth or ground. Brown is our live or hot, and blue is our neutral. So we connect those to connect our live and our neutral to our relevant terminals here in the PDM, and we just connect earth or ground to our chassis, a convenient location on our chassis. And in this little mess job here, you see this is where our single phase AC wiring connects to our charging socket. This is a CCS type 2 from some Kia or Hyundai car. So we've got our single phase AC, which is our 3 terminals here. We've got our PP and CP, which we showed you earlier, on the red and the black wires just going straight to the PDM. And that is our setup, folks, between charging, supplying 12 volts, got our VCU up there, coming down into our wiring bundle, finally over to our PDM. All right, so we've got 2 more things to show you before we can get into the real fun. First is this little 3-way switch here. What is this doing for us? Well, oh look, Gomcat, it's you. Gomcat has came in to say hello to us, folks. I know there had been some concern about the GOM cat's well-being in recent videos, and I appreciate that, as does he. But as you can see, he is in fighting form and ready to get back to work hacking OEM components for us. Isn't that correct, GOM cat? Now, GOM, I'm trying to explain the VCU to the folks here, so why don't you head back inside, get some sleep, and I'll catch up with you later on. Now, here we go. Sorry about that, folks. GOM just reappeared. Now, what is this? Well, these are just light switches like you'd have in a domestic house. So turn the light on, turn the light off. I'm just using them in this case to control some of our digital signals to our VCU. Got a red wire here, just a 12 volt battery positive. I've got some wires here from our VCU. I have our forward input. I have our terminal 15 input. I have our start input. And I have our high voltage request input. So in this case, when we turn on the first switch, we just apply 12 volts to our forward input and to our terminal 15 input, thus telling our VCU that we would like the motor to turn forward. We are on an ignition on position now, so we're getting ready to crank up. And finally, in our second little switch here, thank you, GOM. Normally what I do with this is just give it a flick, which would be akin to giving it a flick of a start momentary terminal. And at that point, assuming conditions are met, the VCU will initiate pre-charge. If pre-charge is successful, we'll close the main contactor, turn on our inverter relay, and we're ready to go for a drive. Then when we come back home, switch off, turn our key off, and the system shuts down. And in order to tell the VCU how much torque that we would like from our motor, we of course need a throttle pedal. This is a throttle pedal from kind of mid-2000s BMW. It's on various models. This is the one that I generally use because, you know, kind of cheap, easy to get at my local scrapyard, and they fit most of the cars that I'm working with. So this is a 2-channel Hall effect pedal. It has a 5 volts, ground, and 2 signal channels that we connect to our VCU. So when we push our pedal up and down, we get 2 variable voltages generated by the pedal, which our VCU can then interpret as a driver torque request. We'll turn that into the relevant CAN messages and transmit them to our inverter, and with whatever kind of throttle ramps and limits that we will have set in the VCU. Also, the VCU will detect things like if we're parked and we want to do something like charge the car, then when we insert our charging plug, like so, it would, assuming conditions are met, so we're not in drive mode, etc., initiate pre-charge. Pre-charge is successful, bring up the power to the PDM, lock out the inverter from drive mode and commence charging based upon a combination of the parameters that it gets from our charging cable and those set within the VCU. Okay, so we've got ourselves a throttle pedal. We have that connected to our VCU. So one of the first things that we're going to want to do once we get our VCU hooked up and has power to it is calibrate our throttle. So in this segment, we're going to describe how to do that. So if you want to know the details of the connections for connecting your throttle pedal, then please see part 2 of this video series. But just to briefly recap, there are 4 connections: throttle plus 5 volts, throttle ground, throttle channel 1 and throttle channel 2. This VCU allows for the use of either single throttle channel or dual throttle channel, and has got error checking both between the dual channels and for throttle out of range errors. So let's start by going down to spot values. We'll scroll down here until we can see our parameters for pot and pot 2. And we just hit our refresh button here just to make sure that those values are current. So pot is reading 219 digits and pot 2 at 438 digits. And those are just the raw values being received from the analog to digital converter in the STM32. And are typical of what you will see on one of these Hall effect throttle pedals, in that one channel is usually about half of what the other one reads for safety purposes. So the first thing to do is we're going to select auto and click refresh once. And what that will do is it will continuously refresh all of the parameters. And indeed, you'll see there's a little change in the pot values there just due to noise. Now I'm going to move the throttle pedal here just over its full range, and you guys keep an eye on those values. You'll see that they're slowly increasing until we reach full throttle, and then they'll decrease as we come back off our throttle. And that shows us that we have a functioning throttle pedal. So let's go ahead and untick auto and just click refresh once more just to go back to normal. So what we're going to do now is we're going to note the values of pot and pot 2, and we're going to add roughly 10 points to them. So let's say pot, let's call it 220 for a round figure. So let's say pot value, the pot min value that we're going to enter will be 230. And let's say that pot 2, just again for the sake of a round figure, is 440. So let's call that 450. So 230 and 450. We're going to go to parameters. We'll scroll down here. We have pot min, which is currently at 220. So we're going to set that. And I always forget this. I just always do. Let me go back again. If I actually made a note, it would be a good thing, wouldn't it? Apologies, folks, just a bit of life getting in the way there. So we said pot 220, and we're going to add 10 to make it 230. So back to parameters. We'll go to pot min, and we'll set that value to 230. 230, and press enter. Always press enter when we change a value. Back to our spot values again. Pot 2, let's say 440, so we said 450. So back to parameters, and we say pot 2 min 450, 450, press enter. Go back to our spot values and back to our pot. There are 2 pots in the middle. We're going to go back to, oh no, sorry, we're not. We're not going to go back to auto. What I'm going to do off camera now is just press the throttle pedal all the way down, holding it at full throttle, and press refresh once. Now, we now have our max value. So let's call it 1250 for pot max. And let's take 10 points off that, and we'll call that 1242. Let's call that 1242 for pot max. 1242. 1242 and press enter for pot max. We'll come down here now and we go to pot 2. Or is it gone? Here it is. So 2507, so let's call it 2500. Back again for pot 2 max, 2500. Press enter. And don't forget now, we want to come up here. And our next thing that we want to do is ensure that we're in, because we have our 2 channels selected, we want to ensure that we have a dual channel throttle selected here. Okay, let me rephrase that. Because we have our 2 channels wired up and calibrated, ensure that we've our dual channel selected. I'll come back in 1 second to you for single mode. I want to check that our messages have got set OK. We're going to come up to our parameters. We're going to click Save Parameters to Flash, as we know what to do then from our last video. Come back down to our messages and we say parameters stored, and we have our 32-bit CRC value. Now, there's a little gotcha here in this about using single throttle mode. So our little menu here under pot mode has got dual channel and single. Obviously, you know, I would recommend that you use dual channel because, again, I think most throttle pedals have that facility. But if there's a reason, just for simplicity or a bench test or some particular legacy system that you're trying to work with, you can indeed select single channel. Now, the catch is that if you just select single channel, but you have wired up a dual channel, and maybe calibrated or even not calibrated it will not work. So if you are using single channel mode, only wire up 1 throttle channel. That's super important, folks, okay? So we'll go back to our dual channel here for the purposes of running our system on the bench. Okay. So now that we're set up here, let's go ahead and run our motor. So we've got our high voltage turned on. It's being supplied from the Land Yachts demo port at the minute because I no longer have a kind of a bench battery. So that's giving us about 390 volts into our system here. So I'm going to go ahead now and we're going to start up. And we're going to just run the motor just to get our feet wet here. Pun intended, because it is rather a wet day today. So, quite simply, I'm going to turn our ignition switch on. So that's turning the key to the on position. I'm just going to flick this middle one here, which is the equivalent of just turning the key against the spring to the start position. You'll hear a few clicks. That's our pre-charging system working and our main contactor closing, and our little relay kicking in here that's applying the switched 12 volt power to our PDM and inverter. If I take our freshly calibrated throttle pedal, press it, our motor spins up. And you're going to see that we have regen. And that is very much thanks to the efforts of Johannes. A little bit more tuning to do on it, but just thought I would introduce that fact to you. So that is a very simple test, but we will go through now. We're going to go through 2 things. One will be just some of the tuning parameters that we can do on the web interface. And secondly, we will do some of the gotchas or the catches that can affect people and stop them getting to this first spin of the motor situation. So to turn off, then we just turn our key back to the off position. And everything shuts down just like that. Alright, so we're here now with our web interface, and we would be going for what could be, I guess, a first test run of our drivetrain here on the bench. We've got our high voltage available, we've got our 12 volts available, and we're communicating away happily. So what I would first of all do is select auto and click refresh here so that we're constantly updating the parameters here. So what's the first one that we should look at? Well, the first one is always op mode. Op mode is currently off, which is perfectly fine. The next one is last error. We're saying none, so there's no errors. We will generate some for you fairly soon, but at the minute we're in a non-error situation. Status, UDC below UDC SW. And what the VCU is basically telling us here is that the voltage that it's measuring with the ISA shunt, currently about 7 volts, is below the set point that we specified in UDC SW, which is the voltage at which we would like the pre-charge to finish and the main contactor to close. So that's perfectly fine to have that error here, or status I should say. So let's scroll down here. Now the web page will jump a little bit here when we're moving it like this with auto on. And so we have inverter is Leaf Gen3, which is perfectly fine, and vehicle is set to classic. Now, the next one that we want to look at is T15 status, which is our ignition on status. It's currently off. So we're going to flick that to on. So now we have T15 status on. So we've now confirmed that the VCU has received the message that we would like to start up. So we're going to go back up just to the top of spot values here. And I'm going to hit my start button. Now you see here that op mode has changed to run, last error is still none, and status is now none, which means that we have no errors and no status problems. We're seeing the full 390 volts available here in UDC. Now at the minute, we're not drawing any power, and we're not drawing any current as far as our shunt is concerned. But that should change fairly soon when our DC-DC converter in the PDM starts up. And if we come down here, we will see our inverter UDC is reading slightly differently, but that's perfectly fine. And it is reading the voltage that the inverter is measuring and transmitting that via CAN to us. So that means we've got good communication with our inverter. Now if I take my throttle pedal here now and just spin up the motor, we're going to see some other things changing here. Apologies about my power and current readings here. That's something I need to fix. But you'll see here that we're getting speed, which is the motor RPM, which we can hear. And most importantly, if we come down here, we look at our pot nom, we'll see that value change as I press the throttle. And indeed, as the VCU calculates the regen that we want to see. And you'll see the torque value changing from positive torque and negative torque values for regen. and of course the pot for our analog throttle changes as well there. Alright folks, so apologies for that. I had this particular branch of the software that I'm working on at the minute had a little bug in it that wasn't giving us our currents and powers and all that, so we've now got that fixed. So we're on auto refresh here, so we can turn our ignition on, hit our start, and we'll see that our voltage comes up. Let me just scroll up here a little bit, so hopefully you should be able to see power and current there. As soon as the DC-DC starts up in the PDM, there it goes. So we got about 150 watts of power consumption there from our PDM. And if I press my throttle now, see a little bit of regen went in there. There we go. So that's our power read from the ISA shunt and current read from the ISA shunt. Also we get kilowatt hours and amp hours from our ISA shunt, and should be obvious there we have speed, which is our motor RPM, from our ISA shunt, or not from our ISA shunt, from our can from the inverter. So this is what a typical running system, at least for our Leaf stack here, would typically look like. As I said, we've gone through our pot and our pot nom and all of these kind of things here. Other things you'll see will be things like heatsink temperature, motor temperature, auxiliary temperature comes from the ISA shunt. The UOX is the 12 volt voltage measured at the VCU, a few other things like that. But that's, if we come down here a little bit now, we'll see that our forward direction is selected on. It's very important to have a direction selected, because if we do not have a direction selected, then we do not drive anywhere. So what I'm going to do now is I'm going to just take automatic refresh off, and I'm going to do a few things here that can cause us to get no rotation of our motor. So I'm going to switch off our ignition so our contactors drop off, and just off camera I'm going to just do something here, and we're going to go back up our main spot values function here, go back on to automatic refresh, and we should, yeah, there we go, we're in off mode. Let me bring you up here, and we're again very same situation. Now I'm going to press our ignition switch on, I'm going to flick my start, we hear our pre-charge come in, we go to pre-charge op mode. But now the pre-charge contactor has dropped out, and my last error has changed to pre-charge. So what that means is that I have no high voltage available. And what I did there was I just disconnected the high voltage supply to our test setup here. So we just want to turn our ignition switch back off. We'll fix the problem. So we'll basically re-enable our high voltage supply, put our ignition switch on, and flick start. And we go back, we're into run mode, and if I press the throttle, there we go. We're back running again, and probably starting to draw power, yeah, from our PDM. So this is what will happen if we get a pre-charge error. The pre-charge timeout takes 5 seconds. So what that basically means is that if the voltage we read here on UDC does not exceed the value in UDC SW within 30 seconds, we basically time out on a pre-charge error. So it's a common little gotcha. So let's see what else could cause us to have a problem, but would be a little bit more harder to find. So let's come up into our, I guess everything's unfortunately dumped under throttle here. I really do need to break these guys up a little bit better. So there's some parameters here. One of them is UDC min, UDC max, and UDC lim. So what do they mean and what do they do? Well, UDC min is the minimum voltage at which we will allow the inverter to generate torque. Now we've got it set to 280 volts here. But let's say that for some weird reason that this was to be set to a rather high value, let's say 480 volts. What would the result of that be? Well, let's go and have a look. So back down to our spot values and go back on to automatic, refresh, and we'll go back and we'll put our ignition was, we were on all the time. So anyway, okay. So let's go back for ignition on and go for start. Now we go into run mode, perfectly fine. 390 volts. Come along. Oh dear, what's going on? We're in run mode and we're pushing the throttle, but there's nothing going on. Now, how do we diagnose this? Well, we come down here, we look at our pot nom value when I press the throttle. So I'm going to come in here, there's my throttle. I'm going to press it all the way down. And my pot nom just does not go positive. You see, it will go negative, as I would still be allowed to regen, because that's under a different parameter. So with my throttle all the way to the floor now, pot nom is 0. If I release it and go back to 5%, because that's my commanded regen. If I look at my torque command here, it's currently 0. Push my throttle all the way to the floor, still 0. Now we know, because we've obviously changed that UDC min value to a voltage that is above the value that we have available. So UDC min is basically saying to us, we're saying that unless we have a minimum of 480 volts available to us, we will not allow positive torque. So let's go back and change that. So here's our UDC min. We'll put this back to where it was at 280 volts. So 280 volts. Now, if I say UDC max, which is at 420 volts, UDC max is the maximum voltage on the battery, measured by the ISA shunt, that I will permit regen torque to be commanded. We've got 420 volts, but let's say some naughty person came along and set that to 320 volts. What effect will that have on us? Well, let's find out. Let's go back to automatic, back on to refresh. We put our ignition on, we'll kick our start. And as you can see, we're in run mode. UDC is at 390, so let's give our throttle a little press. And we can generate torque, we can spin. Oh, but look, there's no regen. Our motor is just spinning down by itself. It's, as we can see, there's our RPM. There's our torque is currently 0. But let's have a look at what our pot nom says. Our pot nom says 0. We're not going to the negative 5% that we had previously, because what we have said to our VCU now is if the measured battery voltage is above 320 volts, do not create any regen torque. So let me just do that one more time. I'll push the throttle. See, a little bit of pot nom goes positive, but when I release the throttle, then the motor is basically coasting to a stop here because we are not allowing any negative torque. Now, so there's the workings of UDC min and UDC max. Let's go and reset these to sensible values. So 420 volts. Enter. UDC lim is probably a little bit of a redundant parameter here. It is a kind of a backup to UDC max. And what we say is that if the voltage ever goes above UDC lim, we don't just zero out all the torque commands, but we shut off all of our contactors. So don't think there's any real need to demonstrate that. IDC max and IDC min are our maximum torque. IDC max is the maximum positive current that we'll allow to be drawn from our battery, and IDC min is the maximum regen current that we will allow. So TMPHS max is our heatsink maximum temperature. Now, currently I don't have any cooling on the inverter and the motor here, but that's no big deal because we're just doing little tests. But let's say that we were to have a cooling system failure, and or this value was set to a rather stupid value, let's say 10 degrees centigrade. So if we set TMPHS max to that, let's see what that does for us. Let's go back to our spot values, back to automatic, and hit refresh. And we put our ignition switch on, pre-charge and start. We're in run mode. Let's go ahead and press the throttle. Oh. And indeed we do generate torque. So let's scroll down. So TMPHS is at 16 degrees centigrade here. And we have specified a maximum, I think, of 10, unless I didn't actually set. So I do seem to have myself a little bit of a problem there with that. Did I set it? Oh, I didn't set it. I'm in a complete clown. All right, because minimum is 50, so I can't actually set this to any lower than 50 degrees. So I kind of shot myself in the foot a little bit there. So that's kind of self-correcting. You shouldn't be able to do anything too silly with that, as I just discovered for myself. By default, it's set to 85, which is kind of a sane value. So the next two here that can cause us a problem are trot min and trot max. So let's switch off our system again here. Let's change trot max to, oh, I don't know, let's set it to 0. What's going to happen if we set trot max to 0? And we go back to our spot values. Automatic, crash, key on, start up. And let's press our throttle and see what happens. We're in run mode. We've got, when the last hour was pre-charged, that's fine. I'm pressing the throttle. Oh no! Oh no, there's nothing happening. So, again, how to diagnose any of these problems. We come down and we look at our pot nom. Now our pot nom is at -5% because we are allowing negative torque here. If I floor the throttle, we go to 0. But if I go up to my torque command is still 0. I'm not commanding any torque here, even though as you can see, our pot values are hitting max. Our pot nom is only at 0. So we're not allowing any positive torque generation. So those are some of the little gotchas that can stop something from running, even though we are in, strictly speaking, run mode and do not seem to have any errors going on here. This is probably something that we could improve upon at some point in the future. So again, obviously these can be set to, sane values here for limiting during testing and things like that. They're quite useful for. So again, now we're back to 100%. And we're indeed running our motor again. So, couple of little pointers there for you folks that can easily cause a problem to people that wouldn't be familiar with how the system works here. Alright, so the next thing that we're just going to demonstrate with our little test rig here is going to be charging. So in the case here, we have several different charger interfaces that we can use. We have none, i3Lim, CHAdeMO, and Leaf PDM. So what does that mean? I'm not going to go into as much detail as I did in the last video here, but it basically means that the VCU will use the i3Lim, its internal CHAdeMO interface, or the Nissan Leaf PDM for handling battery charging and communicating with things like the charging point EVSE. So in our case here, we're going to select Leaf PDM on our menu. We leave power set point where it is at the minute, leave IDC term and the rest of that stuff where it is. Charge modes, I think we just put into off for the minute. You can put, actually, sorry, I tell a lie because we're using the words that need to be an external cat. Okay, folks, so one of the things I want to deal with in this segment is problems that people have with connecting to the Wi-Fi, maintaining a connection to it, and upgrading firmware. So, as you'll see here, we've got our VCU powered up and our computer is connected to it. In fact, the computer is not actually connected to the wireless access point that the VCU is creating. You have a choice in that you can configure the Wi-Fi module to create its own SSID and passphrase and then connect to it, which is what we do when we're in the cars and out and about and stuff like that. But when I'm here at home, what I find works a whole lot better, particularly during the summer season here, because it's mostly holiday homes here, and during the summer season everyone's got Wi-Fi, everyone's got phones, everyone's watching Netflix and all that kind of thing. And it was one day here in particular that I was literally here, and for 3 solid hours I could not get this computer to connect to this VCU. It did not matter what I did. Sometimes it'd connect, sometimes it'd drop the connection, sometimes the Wi-Fi would drop out. Sometimes you could try to do a software update and get halfway through it and you get hung. All kinds of problems. But here now, today, I've been trying for the last few days here to actually generate this on camera for you folks so that I could show you what actually happens and how to circumvent it. But here, it's just going to blast away. It's just not going to have a problem at all. So that's us updating, connected just through the home Wi-Fi network here. But we can do the same thing. So let me just connect the computer here directly to the access point that the VCU is creating. That's it there. Connect. It's connected. It even connects so quickly, you just know you're going to be fine. There it is. Update. There's our bin file. And update, and it'll just do it. And I've tried all kinds of tricks here to try to get it to fail, like cutting off the power in the middle of the update and stuff like that. But it's just, don't tell me I managed to catch it. Did I seriously manage to get it to hang? Please tell me I did. Okay. We're in a hang. Yes, baby. So, how do I know that? Well, the first thing is that my activity LED here has stopped flashing. And if I were to refresh my web page here now, I will get the web page back, but there will be no data, so there's no parameters here. So I'm delighted with this. I was literally unbelievable. All right, so first thing to do here, if this occurs, is cut the power, count to 5, and put the power back on. So let's try that and see if that has any effect. And it does. Damn it. So we've just rebooted here, and we probably even maintained the connection. Let me just recycle that. Yeah, there it is. We're basically back on, and we've got our parameters back. So that's, again, connecting directly. So we're now connected directly to the VCU. Now, one of the things that happens is that, and I've seen some folks commenting about this on the forum, that it sometimes works better if I have the computer near to the VCU, or if I have to cover off the VCU and that. Now, I can go ahead and I'm going to just whip this little screw out. I've just got a screw in here to stop this falling off the workbench. So I'm going ahead, I'm going to pull that screw out, and I'll pop the cover back on here, and we'll basically do the same thing again here, because I want to just kind of demonstrate what, if I can't show you what does cause it, at least I can show you what does not. And as it stands now here, I can walk out all the way down to my front gate, which is about 20 or 25 meters. And I can do software updates over the direct Wi-Fi connection here. So, all right, that's our lid on the box. I'll just put something on top of it just to, really make sure that it's sitting down. And let's do a software update here and see if we can get it to screw up. Let's see if it's screwed up. So we're going to hit our refresh. And that's interesting. Have we actually got it to screw up? Let's pop the cover up. Yes, we did. We actually got it to hang. So, let's power off. Count to 5. Power back on again. And we're back. There we are. We have connectivity. So, let's see what else we can do here. Here we see the gome cat in its natural habitat. We must be cautious, or it could attack if provoked. The diet of the wild gome cat is premium cat food of very expensive sort. As we can see, a token effort was made to cover it before claiming the main seat in the workshop. The gome cat must now not be disturbed at any point, or again it may attack. We will retreat to a safe distance. Alright, so I brought the computer out to the workbench here. We're just a good bit away from it, and we got a concrete wall between us and the VCU here, and rather annoyingly, it's just going to update. Of course it is. Now, it still seems to prefer to need a reset here when we do this method, which is kind of strange. Yeah, it's going to need a reset again, I think. So let me just do that. Alright, so I just reset the battery there. Let me just do another, see what we get this time. Or have we dropped the connection? No, we haven't, rather annoyingly. So there it is. So let's stream a little bit of live data even here from this team. Try to put it under a bit of stress. Just go for automatic, go for refresh. And it's it's basically streaming. And we're just connected here. I'm out in the, just out in the workshop area here. The gome is keeping an eye on things, and our VCU is inside here with the lid on and a bottle of cutting compound sitting on top of it. So yeah, this is the super weird thing about this, is that, are we still streaming? Yes, we are. So you might reasonably ask, what is the cause of this particular problem? And it's rather simple. As I say, if we're in an area that has particularly strong Wi-Fi signals, or a lot of them, the Wi-Fi bandwidth, the 2.4 gigahertz bandwidth, can become very constrained. And as I say, I've seen that happen here. I cannot generate it on the demand, but it first showed up here for me in around 2019. And I can pretty much track it by when a lot of the holiday homes here are occupied. So what I suspect that folks are seeing is that they're just in areas that have a lot of active Wi-Fi connections. And it may not even be Wi-Fi, because these days now there's a lot of these area broadband services that are operating via Wi-Fi as well. I know we have, there's two particularly strong Wi-Fi networks here that just broadcast into every nook and cranny of the building, and they're one of these kind of wide area Wi-Fi networking type things. And they definitely cause me problems, but not as many problems as when neighbors' houses are occupied and so forth. My recommendation is, if you're having this problem persistently, then use the option of connecting your VCU to your own home Wi-Fi network, because then at least you've got the benefit of the fact that you've got your own router helping to boost the signal to your laptop or desktop or whatever it is that you're trying to communicate to the VCU with. So that's just a little bit of advice on that one, folks. My apologies that I cannot generate this here. I have tried. Like I said, it's, believe it or not, it is just not something that you can generate by deliberately, you know, like cutting the power during a software update or resetting the STM32 during a software update, or even uploading the wrong software onto it or something. It's I spent a good bit of time here, and I even had some footage of this, and all as I ended up doing was proving how friggin' robust that the system is. And I know that, as I say, there's some folks struggling with just basic connectivity. So that is about what I can do for you on that subject at this time. Okay, folks, so in this segment, we're going to show you how to initialize your ISA shunt using the web interface of the VCU. So I'm at my little test setup here in the office. Got my VCU, got my shunt, there's a little PP3 9-volt battery there just for demonstration and testing. So we're going to assume that you've got a new shunt. So we've not initialized this. So what does that mean? Well, by default, these shunts come from the factory without all of their features enabled, and with the data format of the CAN message in a different way to what we want to see in our VCU. So we now have on our firmware the ability to just do an initialization. So I'm going to walk you through that now. So first thing that we want to do is come down to our communications subsection. You'll see ISA mode. Now by default this should always be in normal, but we're going to assume that we have a new shunt here, so we're going to change that to init. We're then going to hit our commands button and go save parameters to flash and confirm that we have stored and we got a CRC. So now what we're going to do is we're going to power cycle both the VCU and the shunt. Now basically how you should have this wired up is that your shunt 12-volt supply and your VCU 12-volt supply should be on the same line. So I'm just going to turn off my bench power supply. Just give it a few seconds and I'm going to power it back up. Now at this time we will be initializing our ISA shunt. Let me just check that that's actually, yeah, there's our CAN messages. I was just monitoring on another screen. So we'll just go ahead now and refresh our web page. Sorry about the Volkswagen engineers, they're a bit angry. We'll now change init back to normal, go back to commands and save parameters to flash. If we come down to spot values now and we do a quick refresh, there we'll see we have 9.4 volts on our voltage 1. If we move this little tab over to voltage 2, click refresh, yeah, there it is on voltage 2. And just over onto voltage 3. Yeah, there it is on voltage 3 as well. We should have our temp aux reading the room temperature, which is rather high this morning, 23. So that is now how we set up our ISA shunt using the web interface and our VCU. So there's no need for any other messing about. This is something that I did, rather silly of me to overlook, but we now have that in the latest firmware. That release will be available on GitHub, hopefully by the time that this video is out. Okay, so in this segment here, we're going to just very quickly demonstrate regen. It actually took quite a bit of work to get this working well. So big thanks to Johannes, because he really helped me out with this. So we're currently, the parameters are that I've got 6,000 RPM rev limiter. We're at 30% regen max and 30% regen travel. Got my throttle here, so we can now regen right down to a complete stop without any oscillations of torque or motor not doing what it should do. So that is our regen, and that's in the current code. So the next thing that I'm going to do is I'm going to demonstrate with our Leaf PDM here, automatic charge starting and stopping. Alright, so I'll leave you folks watching the screen here. As you can see, we're currently in off mode, and I'm just going to take my Type 2 plug here, stick it into our charging socket. You'll hear our pre-charge kick over. You'll see our system start up, our DC-DC comes up, and then followed immediately by our charger. At the minute, we're just using a little granny cable here, so it's quite low power. And then when I go ahead and remove the plug, we basically shut off. So that's automatic charge start and stop via our Leaf PDM, and I can just, if you want to see me do it, I guess here with the plug, we can just do it here again. This is my, whatever it is, Kia or Hyundai socket. It's just going over to our PDM. Let's plug in. Here are the clicks, and there's our DC-DC. We are charging, and then we want to switch off. Just plug out, and that's it. So that is our Leaf stack here, pretty much working very well. We've got drive, we've got regen, we've got DC-DC, we've got charging. We got pretty much everything that we would want from this guy. So folks, that's it for part 3 of our VCU user manual series here. I hope that it's been of some use to you and helps to clear up some of the, at least the more common questions. I know that at the minute we're really struggling with the chip shortage, that the kits that I'm sending out do have components that need to be fitted. So that is an unfortunate aspect. It wouldn't really matter where I was getting the boards made. We would still be stuck with pretty much the same thing. So with a bit of luck, come, I guess, maybe 2022, we will start to be back in a position where the boards that we supply have all the components on, and you're literally just soldering the header on there, which is a simple through hole job. So Anyway, folks, I won't say this is the last part in our VCU series. There'll probably be another few parts because as things progress and as I try to, I guess, encompass as many things that people need to know. So as usual, I'd recommend anyone coming into this to check the links in the description, particularly as they pertain to the VCU. So like the wiki page, the GitHub page, the support forum and the the support thread and the development thread on the Open Inverter forum. So I will wrap things up there for you. Don't forget to dislike, unshare, do not subscribe to this stupid channel, and for Pete's sake, don't follow the links in the description and support me on Patreon or PayPal, because then I just do more of this junk. So with that being said, from the Gome Cat and myself, happy Halloween, and also happy ISA shunt initialization.